In this lecture 13, I will review the concept of geometrical condensation that we talked about previously, and then relate this concept to the condition of full chain stretching. Subsequently, I'll move on to chapter 9 on shear bending. I will motivate this topic by reviewing the historical and theoretical background. And then I will move on to start to describe the technical aspects of making particle tracking velocimetric observations of shear bending using untangled solutions.
Do a little bit of a review because last time we are sort of a little bit stuck on this point, but I still want to drive home this basic concept of geometric condensation. So this geometric condensation is just a way to recognize that the wall chain comes as a coil. And when you try to introduce the concept of how many chains coming through, if you use a surface to cut, you find that each of the time it comes to a surface, it will occupy a space of S. And last time I also indicated not all the angles are coming in vertically. So the area it occupies is actually a little larger than S. So you can say maybe larger than S by a certain amount, so that the concentration, the area density is smaller. In other words, alpha will be smaller than 1. Or if you like, the effective area, let me maybe use the effective cross-section is actually a S. That's larger than the original S. So in that sense, what we have is really this new S. It falls back Q times, and there are Q number of chains, and that satisfies 2 pi RG squared. And since we have defined the number of strands per unit area, the number of chains cutting, passing through the area per unit, the number of chains, let me rephrase it. When you have a chain of size Rg, as a Gaussian chain, if you imagine a plane cutting through it, you'll find the chain will visit this cut-through plane several times. And you can also ask, really, how many such chains per unit volume do you have? And that's this quantity. So this part I introduced last time already. And this would mean that effective times Q times phi is 1. So which is what we had last time, except I didn't have that modification factor here. So I just want to repeat this part, that the only time the number of strands, number of chains coming through the surface per unit area, the only time this could be, and this number is now what am I doing here? Phi is 1 over S infinity. So from this equation, this ratio is nothing but Q. 1 over Q, sorry. Of course, it's a smaller than 1 quantity. So the only times you could have chain really going through the surface only once is for the chain to unfold. to be fully stretched. Okay? And on the other hand, this expression, because we know this quantity, we know Q, we know SF, so we know this quantity Q is nothing but 3/4 square root of 6 lambda star. And now I'm introducing this extra factor of alpha because of the fact the chains do not come to the surface all vertically. Some are projecting a much larger area, as shown here. So this indicates, as I last time tried to say, if this prefactor is 1, I have a very clear conceptual description of what's going on. I can stretch my chain by a factor of lambda star. Then the number of crossing at the surface will reduce to 1. And this will come to 1, and Q will become 1. Oh, sorry, in that limit, what did I do here? Yeah, I need to go one more step to do that. I was too fast. I need one more step. So Q, which is equation trying to find it for you, which is equation, last time I showed you too, equation 2.39b when we talk about percolation model. I know we didn't go through, but the book went through it. I just skipped this part of the result. Except for this factor of alpha, this is the result. It tells me that Q is related to the maximum stretching, which I introduced here, like so. So now, as I stretch, my area will change by a factor of lambda star if I think I can stretch this coil to become fully aligned, fully stretched. Then, in the fine limit, you will still have as many strands as you had before. So in this affine limit, which is what we do, your phi will also increase by lambda star amount, okay? And this new phi prime is something you can compare with the ultimate stretching limit, which I told you is 1/Q. So if I plug this 2 in, sorry, I'm just too fast here. As usual. So I can take this ratio. This ratio is lambda star phi, not phi, what is the name? Psi. Huh? Psi. I'm just plugging this result. This part is 1/Q. So it's lambda star. Oh, Lord. It's trying to save it. Auto. So this is the result. in the book, we had this, basically Q is alpha 3/4 1/6 lambda star. So it would be lovely if this is unity. Then in this limit of affine deformation, this will go to unity. Then it means all my coiled chain is straightened and look like a chopstick lined up, cutting through the plane now. And this number, of course, is not unity. For example, this number is 1.82 or 84, 1.8 something, and times alpha. But alpha kind of helps me here, because alpha, remember this chain, if it vertically come down, it projects an area of S. But since it can come down at an angle, it actually projects a ellipsoid. And you can calculate that projection is essentially related to the original S divided by, so if this is theta, divided by sine theta. And that is my alpha. So this sine theta is alpha in the definition of the previous page, right? Here. Okay? And which is, of course, always smaller than 1. So I can make a bold guess. I can say, maybe I can take an estimate by assuming that on the average chains are at 45 degrees. Okay? And that will give me this whole quantity will be 1.8 divided by square root of 2. And that's getting close to 1. So I'm just trying to achieve a conceptual understanding that when I claim I can fully stretch the chain, that should also be the limit I no longer have any fold. And in that limit, this number will go to 1 because it will come across through the plane only once. And this discussion is really, truly new, meaning I don't think you can find it in the literature, so I'm repeating this a second time, really, to make sure that it is of great importance. For example, you graduated from this course in the future if you want to think about the mechanics of your polymers. And that all speaks about how to think about how processing can change your structure. And this is a case of affine deformation, as I indicated. Of course, in reality, nothing is affine, but it's okay for us to simplify our discussion here. Okay. So, any questions? I think I would definitely invite you to reach me privately for any of questions on this point. As a recording, whatever I said is sufficiently clear. It's just a matter of taking time to digest it. So let's move on. I'm showing you the outline one more time. So we went through, we concentrated on this point here, the geometric condensation. So we're more or less done with chapter 8, and we're going to move on to chapter 9. And not to forget any of the things that we have. So with this chapter 9, which of course you have seen for convenience, I copy it here. You have seen this moon wave before. this is a section, this is a chapter that concentrates on this phenomenology here. And keep in mind that this observation was largely the reason for us to revise our thinking about nonlinear polymer rheology and eventually develop some theoretical concepts. But let's get back to chapter 9 on basically shear banding, which is done. I will go through some details about this technique, particle tracking, velocimetry, with symmetry. But before I even begin, let me give you the background. I think at one discussion, you guys, no, it was in my other teaching class. This is when you teach two classes, it can be at the same time. It can be really confusing what I said in which class. So the question to ask is, are we on Earth really the first one? It doesn't do anything like that. Because it has a extended, oh Lord, I shouldn't have done this. It's giving us, it's converting. So basically the question was, are we the first one to come up with the concept of shear banding? The short answer is no. Are we the first one to observe this shear banding? The answer is slightly more mixed that I need to indicate. But more importantly, let me say first thing first, the concept of shear banding. Did we invent this concept or discover this concept? And the short answer is no. Okay? And here is all the interesting science began. It was an incredible story. So let me be patient with you on this point. As you know by now, Lord, where did I have it? I had it once before. I needed more than once. Here, I need to borrow this spaghetti or crystal noodle again and again. This is our classical picture. You know, our polymer is a complicated object like this. If you magnify it 1,000,000 times, okay? If you know, because it's nanometer scale. Now I'm magnifying. Now I look at my crystal noodle that you can find in Chinese store. I don't know in India we have that or not. Very thin, transparent noodles. Really a millimeter range. So it's really 1,000,000 times magnified. It look like this. And for you to suggest what you should observe on millimeter scales, that's 6 order magnitude. So I should say this is a nanometer, right? But I blow up a 6 order magnitude already. So for you to say that such small scale could produce whatever you observe on millimeter scales is really impossible unless you have a molecular theory that says, oh, give me these chains on nanometer scales, I can tell you how it should behave on my rheometer, on millimeter scales. So we need such a theory if we were to make any interpretation of what we observe at a molecular level, we need such a model. And such a model did exist. It's called tube model. Developed as early as lastly, more or less, a preliminary version was developed in 1979. I now should also recall for you, let me test your memory. Did I mention about Bryce Maxwell from Princeton? I cannot do a word search. When we talk about yield, I mentioned somebody else had recognized this concept of yield before. Do you recall I mentioned this? Yeah, you do. I hope you do. I think so. Bryce Maxwell. Yeah, I think now I remember telling Travis that he's really the father of rheometry. Actually, he worked with Makosko, who was his student, to build the rheometer. So he already had the concept of that overshoot is yielding. Remember, I mentioned that. Overshoot we already went through. So as a function of time or as a function of gamma, which is fine, which is nothing but shear rate times time. That this is yielding. You know, you don't want to claim anything that's not your invention, not your discovery. So let's be careful. So he did that. When did he propose that? Also 1979. Okay? Also 1979. Same time, a molecular model. So this concept yield is engineering concept. You don't need me to speak about molecules or detailed structure to say, oh, something yielding is happening, right? Because by definition, it's not elastic anymore. It turns into something flow, right? So obviously, the nature of the response changed. That's called yield. You don't need to speak about anything molecular in order to apply, invoke this concept of yield. I want to emphasize that. This is a molecular model, however. There are two features. We will talk about it in much more details later, but there are two features that stand out in this model. Number one, it's a good point to talk about. Number one, based on the same physics that let's say how much I will say today, maybe not a great deal, based on the same physics that I will later explain about shear bending, it predicts overshoot. How about that? Wonderful. It can predict overshoot. My goodness. Meaning, since it's a molecular model, if you can predict something, it means it tells you the molecular origin of why you have this overshoot. In that model, in the way you predict this maximum, I know I'm going to be rather simplistic today about the Thiel model. In that model, in predicting this overshoot, the construction of the model is such you are unable to speak about any structural change. Structural change in the sense of connectivity. And therefore, the idea of calling this maximum yield would not exist. It turns out the origin of this, according to the Thiel model, casually, one can speak about the fact that the chain is over-orienting. Oops. The chains are this chain. Remember your chain initially like this. Now this chain sheared somewhat so that, let me do it right. So this is a chain that has a spherical shape, if you like. By the time you shear it, it will become oriented, yeah? Oriented. become a little bit cigar-like and become oriented. And what do you mean by over-orientation? As you shear more, this axis become a little more oriented. Okay, such that it no longer resists the shear as much. Therefore, the stress drops. Okay, that's the idea. Keep in mind, I think I should say this from day one. In fact, if you paid attention about the repetition idea, remember, I should say this. This model, as many times we do with such a complicated system, is called mean field. In other words, you just look at one test chain and try to evaluate the effect of other chains. What is the effect of other chains? If you recall, it gives you a tube confinement, right? The polymer, your polymer, according to this model, lives in a world of tube. So first thing first, because it's a test chain, because you can speak about any chain, there's no need no longer for you to think about how this chain is interacting with other chains other than there's a tube that's there. And you calculate the stress due to this chain being sheared. It turns out you find the stress drops because the chains become a little bit more oriented. So that it resists less to the shear. So you don't need to speak, you can see, because it's a single chain picture. Therefore, by definition, you don't speak about how this chain related to other chains in terms of our more modern picture, which is not so modern, I will show you eventually. In terms of a picture like this, the chains are hooked because of uncrossability. And I think even mentioned that to you, that this yield point in the zeros order is equivalent to saying, oh, it's no longer hooked, it starts to slide. Okay? And that's a structural change. That is a fundamentally different picture than this picture of over orientation. You get it? Chetan? Yeah? Yeah? Because now you have the light is covered. I cannot see you at all with your hood. Okay. So two things. One, at the same time, they offered a different notion of what overshoot is. It's just over orientation. It doesn't have to. You don't have to speak about yielding or a structural falling apart of some type. I hope I'm not over-interpreting it. In fact, you are here to judge me in that sense. That's all there is. So that's one part. I haven't told you the second part related to shear banding. Related to the concept of shear banding, which I said we were not the inventor of shear banding concept. It exists long before in many other materials, way before polymers. That's all. Nothing is funny in that sense. What's funny is we didn't believe that this can be false for polymers. Meaning this. You do a startup, in absence of wall slip, which we know how to remove it or minimize it or whatever word you want to use. In absence of wall slip, top speed is V0, then half height is half V, and 1/3 of the height is 1/3 of V. It's linearly changing. So it's homogeneous because it means the trying to be fancy, but I don't know if it works. Oh, it doesn't. it still remembers the monitor, I think. In any case, as I showed you here, yeah, this one is doing. The shear rate is the same because the slope is the same everywhere, right? Okay. So why all of a sudden I speak about shear bending? Because the tube model that I'm speaking about here, in its earlier version, had a prescription or had suggested that there should be shear bending. Okay, God, what did we do? This is just happening or happened before? Just now. I'm lost in terms of, does that mean? Hold on. Or can we just pause? Okay. So let's talk about. I did. Thank you. Yeah, I did. I resumed it. Yeah. Let's talk about why the initial tube model sort of prescribed shear bending, or it sort of suggested there could be shear bending. Okay? So this concept, unfortunately, this concept is not new, meaning we didn't discover this concept at all. As I said, many times before, people have, for other materials, people have observed such things. So what happens is the tube model for the same reason it produces overshoot. Same physics. Because this is called over-orientation, double O. The same physics says that in steady state, remember steady state? This is all transient. Steady state, you should remember this. Steady state means, overshoot coming down, eventually become flat. That's steady state, right? In steady state, if you plot the stress in steady state as a function of the applied rate, and of course, when we plot this as function of the rate, we already know this is steady state, so usually I don't even label SS there. It's by definition, if you plot such a thing, you must be talking about steady state, because otherwise you have your otherwise you have your value of stress everywhere. Until steady state, you get a unique value. What they observed, what they predicted, was something very disturbing. Disturbing, okay, meaning troubling. You know what this part is. Well, let's say it doesn't matter. Let's say I even plot it on linear scale. On linear scale, if it's a straight line, what does that mean? Huh? So what this feature means? That stress is linear in shear rate. What is this? Stress is linear in gamma dot. What is that behavior? It's changing linearly, it's increasing linearly with shear rate. What is that behavior? So I tried my best to confuse you. I'm kidding. This is a transient description of what's happening transient involving startup shear. This is a plotted steady state. I'm saying your steady state stress is changing linearly with shear rate. What is that behavior? let me remind you. In fact, I can even give you a hint. This, you are bound to find it as long as your shear rate is lower than 1 over tau, which implies Wi is smaller than 1 on this side. So what is that? What is this being proportional to shear rate linearly? What? Lord, why creep? We're not talking, creep is a concept for constant stress. Well, it doesn't matter creep or not. We're talking about steady state. We're talking about the stress being linear in shear rate. Is what behavior is that? You cannot return this. What is that? Stress changing linearly with shear rate is what behavior? I probably lost you because we never had a formal discussion. I did have a little bit of even Maxwell. Do you still remember Maxwell, the discussion of? Here. Indeed. But you guys should. Indeed, when I discuss Maxwell, I should tell you I have an elastic behavior, that's this, and I have, what is this behavior? Yes. Don't think too complicated. I cannot rewrite history, meaning I cannot say something that is huh? Let me just tie it with you one more time. All the knots together, tie all the dots together. This is shear thinning, yeah? This is the region of Wi smaller than 1. And this region is known as Newtonian because it's one viscosity is constant. Viscosity is constant is what is Newtonian. Newtonian stress is proportional to shear rate. So now you're laughing, right? Because I have no intention to trick you. But you guys should answer it instantly. Instantly. Huh? Newtonian behavior. It's very confusing. You said, didn't you tell me polymer is a shear thinning material? Polymer melt? Yes, it is. But when it is Newtonian, when the rate is small enough. How small is it? When Wi is much smaller than 1. So I threw all the points to you. You should not be confused. That when the polymer is being examined on such a slow rate, such a long time scale, the chains can move around anytime they wish. You don't perturb its structure, therefore its viscosity is constant. Okay. So let's continue. So of course this doesn't happen forever. It keeps going. When I say keep going, don't misunderstand me. I do this experiment discretely. I use different rate, I reach steady state. I use another rate, I reach steady state. And I find, well, probably you can connect between them now. The shear thinning is famously known, so we know this linear behavior cannot persist. Yeah, it must come to an end. If it does, fine. If it does, it would mean it would do this. Right? because sorry, maybe I misspoken. I did. If this is eventually reaching a constant, that means my stress is no longer changing. So this is a constant. Therefore, shear rate will be 1 over shear. Viscosity will be 1 over the shear rate. On this double log scale, this will give a slope of 1, minus 1. Okay, by definition. 1 over the shear rate. It's minus 1 on double log scales. Yeah? That would be the feature. If I can imagine that, what else can you imagine? For you understand this is Newtonian. This is Newtonian. For you, this has become non-Newtonian. But what else can you speculate? Well, I can't speculate much more. Other than the fact that this model speaks about this. Not only that, reaching a maximum and coming down. I know I didn't draw as well as I could. Maybe a little bit too steep, but basically coming down. Okay? Have you ever, look, open your eyes. Have you ever heard of a material? When you shear more, it produces less stress in steady state. At least in the universe I know of, it doesn't exist. In other words, by that I'm almost saying this should be the limit. That blue line. Okay? But this model predict same feature. Look, this maximum turns out have the same origin as this origin. What is the origin of this? Remember, over-orientation, right? So this model basically says in steady state, if you shear much beyond, you know how much this is beyond? It turns out this is not much more than just about 2.3 inverse tau. Not much beyond. It basically says if you want to shear with a higher rate, in steady state, you will have over-orientation. The degree of over-orientation grows, and therefore the stress, the resistance actually drops as you over-orientate more. Same origin. They share the same origin, over-orientation. Get it? Think of 2 ways. One is transiently, when the rate is high, I'm over-orientating. Or in steady state, higher rate gives you more over-orientation, so the stress is lower. This is very disturbing because I try to examine your mind. Material cannot show lower stress when you shear more. That's absurd. Okay? Well, maybe you can say, geez, who told you that's absurd? Why not? But I think there may be even some, I'm not expert on this. I think there may be even some thermodynamic argument or whatever argument one can make about this being unstable or whatnot. I haven't looked into details of that. But basically, this is unacceptable result. Unacceptable. It means your shear will become unstable. Now I can give you the rest of the story. In fact, if you take a more modern view, you will say, if that's possible, this is possible. the dashed line with a negative slope is not possible. Okay? This is in rate, okay? This is not the overshoot that you're seeing over time, over strength. So how material does? A material at lower rate will march on, marching on, marching on, marching on, marching to this point. What if you apply a rate here? Right, beyond this point. Oops, beyond that point. Huh? Remember, this is where the whole thing began. In this background, theoretical background, you have a scenario where if you use rate-controlled mode, oh Lord, where if you use rate-controlled mode, rate-controlled, oh my goodness. Of course, you as experimentalist can wishfully use any rate you wish, right? V over H. V over H. And suppose you apply V over H in here, rate controlled. In this unstable region, so-called. Then you can imagine, gee, something may really go crazy. And system gets stuck. In fact, you may suggest that beyond this rate, steady state, remember this is a plot of steady state. Beyond this point, the stress does not grow further. But you are shearing faster. Okay? How can that be? You'll have one layer that's sheared at the rate of A, or gamma A, and another rate sheared at gamma B. Get it? So that together, so if I plot it for you, it will be something like this. Starting, of course, no slip. We can simply assume that. You have a little shear like this, but in this region, it's sheared like that. Get it? So it's not uniformly sheared here, because you didn't apply a rate here. Okay? If you apply a rate here, everyone will be happy. But you apply the rate here, so the only way to satisfy this is for another layer to be sheared at a very different rate. So that will satisfy. So if you can use different numbers in this region, then this relative thickness will change. So if you call this is F, this is 1 minus F, then this layer, the fraction of thicker one, faster one, slower one will just if you like, let me be rigorous. V over H is so it's basically this plus. How about that? Okay, one unknown, one equation. This equation solves for F, because shear rate A and B are both known. Yeah? Done. When you change it to a different apparent shear rate, you get a different F. That's all. A fraction. Okay? So, isn't that amazing? It's a beautiful picture, if this is true. And at that time, in the mid-2000s, we don't quite know this is true or not. Remember when we are discovering the so-called entanglement-disentanglement transition in the creep mode, it is a time where we don't know this tube model idea works or not. The idea of possibility of shear bending. But we do appreciate if you use rate-controlled mode, you may stuck into this situation of shear bending. When you use stress mode, the creep, the velocity is a free variable. It can go anywhere it wants to go. Right? Why not the system just choose to have homogeneous shear like the green line in the creep mode? Okay? Remember, this shear can be done either in rate mode, which is V over H, or in shear or in stress mode, which is to apply certain stress. And your hope was by using stress mode, maybe the system doesn't have to get stuck. Okay? And it's a different concept, right? And that was the motivation to build a device to see if this is true, to see if shear bending occurs or not. Question? So this part of history is very first-hand, meaning very, very personal, you may say. So, I do require you to have some memory. We had the discussion about in the stress mode, we watch the V over H just rises over time. And we call this entanglement disentanglement transition. And in this rising, I had the perception that the homogeneous shear can be preserved with the background of the possibility of shear bending, proposed theoretically already. Okay? Clear? Okay. So before I move on, I should just mention that there was some observation based on polyacrylamide solution. I indicated in the book as well, just because we definitely don't want to mess up the priority here. So there was a solution that is a aqueous solution because it's in water. It's a water-based solution, where there are some preliminary hint that there is shear bending. I just want to give you the full history of there is shear bending. But the author quickly rejected the connection between the shear bending he observed in this solution and the tube model. Because if there is, you're kind of supporting the tube, the essence of the tube model, because the tube model had a feature of this indicated by the red, and that feature has the implication that there must be shear bending. This is the original paper, 1979. In other words, since 1979, we should be, as experimentalists, be searching for evidence of shear bending. And this one has a clue. But it was eventually the origin of shear bending was understood to be due to hydrogen bonding, some complications in this kind of solutions. In other words, something very special has to do with polymer association rather than polymer entanglement. So not only the work it was neglected, overlooked, but also the author did not connect to tube model because they think this is something special, has nothing to do with entanglement. Just like in other systems that the shear bending is possible. So we have a clean starting point. No experimental evidence for shear bending. Until what time? Until we start to publish our first result in 2006. And we were starting to look at this possibility of shear bending, motivated by the fact if you have creep to produce entanglement, disentanglement transition, at least in that scenario, you should not have shear bending. So we had some desire to look for the absence of shear bending. We also had some desire, thanks to the tube model, to look for shear bending as well, because there is this idea from the tube model that this may occur. Okay? So, but that's between, look how many years passed. That's between, in fact, the paper was published in 2006, but really what we observed is summer 2005. That's a great number of years passed. 26 years. Okay? In between this 26 years, we have one report of shear bending. The rest says there is no shear bending. We couldn't find any shear bending. For reasons, let's see, it reminds me, I should probably make some emails to those folks knowing all this part of history to answer the question of whether people tried and didn't find it, or they tried, the reason they didn't find it is they don't know what kind of system to prepare for, or they couldn't develop the technique, or there was wall slip that ruined their problem, their observation, or what? I don't have a good answer, but I guess I should send a few emails to find out why that it was unsuccessful to find evidence of shear bending. Okay, unsuccessful. And if it's unsuccessful, and we use that word a lot, then this scenario that is in the tube model is a symptom that we should remove from the tube model, because there's no observation to support such an idea. So in other words, can we improve our model such that this does not occur? And this is involve quite a bit of development, and there were ideas proposed, particularly called CCR, stands for convective constraint release. Basically says your relaxation time is going to, or the rate of relaxation is going to accelerate with the shear rate that you applied. Okay? So, so basically, it is indicated, I know I plotted as 1 over tau. So it's indicated that actually the tau is diminishing, it's decreasing. Right? Tau decreasing means 1 over tau is increasing, yeah? So the chains eventually, in this concept, the chains eventually lose entanglement because the shear is bringing them apart, is bringing them out of each other's constraint. So that's the concept. So for a long time, until 2006, we abandoned the original conclusion and suggest that this unpleasant situation would not occur. This stress dropping with shear rate, which implies instability, will not occur. Any questions? So this little part of history, I think I was very brief in the book, but I want to give you a careful introduction of why we start to what motivated us to look into this gap. This gap, H, is 1 millimeter, okay, in a typical scenario. 1 millimeter, of course, is very tiny. Your naked eyes can't see anything. Well, let alone what is you see, meaning what do you do in order to see it? Well, that's nothing, really nothing complicated. Basically, if you have a material, like I know oops, I didn't bring my PDMS here. The PDMS was already, any polymer is a transparent piece of material. Of course, if it's transparent, there's nothing for you to see. But if you put some light reflecting particles, then of course, in principle, when you shine light, it could, the particle could scatter the light. So that's what this is, right? So this gap is 1 millimeter. And the sample is transparent until you add just a few hundred ppm of particles. Very small volume fraction. So it's a fraction of a % of the volume fraction of particles that's light reflecting. And now you can track it. So, so this is a conventional, right, cone plate. This is about 1 millimeter. The gap actually is changing over the radius. And this dimension is usually about 2 to 3 centimeters, okay, in total. About 1 inch, basically. So the equipment, there are a variety of equipment. So there are rheometers. We used to have all the 3 rheometers. You can see on this scale it's tiny, right? 1 inch, actually 2 centimeters is not very large. So this is about 2 centimeters. And later one could build some sliding geometry, sliding plate geometry that I don't need to speak too much about. So at the end of the day, we have, so this is the part that is all discussed in chapter 6. If anything, I should mention this was not, what's the right word? This was not something that scenario immediately come up with. A standard way to do this, probably dictated by the way microscope is configured. If you go to a microscope, right, probably every one of you have seen a microscope. You put your sample on the stage, you have objective lens looking down with a light shining from below, like that. So that configuration probably set up your mind. In other words, for this scenario, the first thing to try is to put our lens vertically, right? Is to put our lens vertically, unlike this drawing, is to put our lens vertically and just looking down into the shearing plane. We tried that. For many months, we tried that. And let me see what I need to do is, let me just use this to explain that. So I know I need to finish. Let me just say a couple words. So you have a shearing plan that's presumably shearing like this. So if you have your objective lens on the top looking down, okay, you have your camera looking down, you will see one of the layers. And if you move your objective lens down a little more, you'll see another layer. Right? You could do that. And if you move your objective lens a little down more, you can see another layer over a gap that's about 1 millimeter. Let's not even worry about light. Well, you can make this two plates all glass. So light, I could have a lamp here to light it up. But this way is actually quite inconvenient because we're not using confocal. That's going to be very expensive. No confocal. If you don't have confocal, then your, I call it Z resolution. Then your Z resolution is very poor. Okay? Your Z resolution could easily be a fraction of a millimeter. In other words, you cannot even actually resolve different layers very well. In other words, if you lighten up, you find the particles, some are in focus, some are a little off focus, some are just all over the place. You cannot have a very sharp image. That's number one. The Z resolution of an objective lens is very poor without using confocal. That's the whole idea of using confocal otherwise. That's number one. Number two, we tried all this. Number two, you lose all your temporal resolution. You have no time resolution. Because you want to scan the red layer, you want to scan the green layer, you want to scan the blue layer, and that takes time. So the only thing you can potentially do is, once again, do it in steady state. That you can. When everything is settled down. You cannot follow the transient. right? You cannot follow if this thing is changing overshoot. You cannot follow it everywhere because you don't have time resolution. So it's very bad for two reasons. Poor Z resolution and no temporal resolution. Or hardly any. So you can only consider steady state. And that will drive you crazy because what you may want to observe is this yield point, is the transect. Okay? So that idea is clearly tried, and as anyone tried, and we tried it first, that too. Just by default, meaning that's how we think about how microscope works. Well, until I learned that not so much that you can tilt your microscope 90 degrees, but rather you can have an objective lens through an adapter directly connected to a CCD camera. So I can have my observation lens pointing at any angle I wish, right? Including horizontally. So looking at it horizontally, of course, means you see every layer at the same time. You look into that gap directly. You see every layer at the same time. And there's, I should just say a word about it. And there's another way that's very, very interesting. Remember, this has very bad. Let me just use this mouse for now. This has I just said this has very bad Z resolution, right? The resolution in this direction is very bad. But we do something clever. We shine a sheet of, we shine a light. So now let's go to a scenario. So here it is. You're going to put your camera now into it now, and it's going to watch inside, and we're going to send a sheet of light, very thin. So only that part, the particle is illuminated. All the other part is dark. So I don't have a Z resolution anymore. I only see where it's illuminated. So the thinness, the thickness, if you like, it determines the resolution. So you overcome that. You can use a objective lens that's $50 to do it. Okay? And of course, if you look at it in detail, you'll realize that this is a free surface. The camera cannot look into it unless you put a film on it to wrap around. Okay? So it's like a cup, right? Basically, unless you have, it's like a cup. You need, otherwise, it's open. See? Right? The cone plate here, come on. This cone plate here, this is all open. There's nothing on it. So we put a little film around it so that it's now. Otherwise, this free surface is not smooth, so you cannot peek into it as you shear. So you need to wrap a film around it. Okay, I think today this is how much I'll stop here instead of going any further. We can have some more questions next time regarding this as we move on. Okay? So let me stop the recording here.